Hello everyone, welcome to Sai Tutorials Jamkandi. Uh, in our tutorial, 10th class Kannada medium, English medium, math, science, English classes are available in the regular classes as well as in the online classes. So dear students, in today's session, I'm going to explain about the continuation part of this chapter, that is moving charges and magnetism. I have explained in the previous session about whatever the concept are related to your syllabus. So we are at the part now. I have completed expression for kinetic energy, cyclotron frequency, helical path of a charged particle moving in a magnetic field, and also uh, so whatever the criteria comes under this sort of syllabus. And now I'm going to derive the expression for motion of charge in combined electric and magnetic fields. So this is nothing but Lorentz okay. Uh, so this is nothing but Lorentz force. So what do you mean by Lorentz force? This is nothing but the motion of a charge in combined electric motion of charge in combined electric and magnetic fields. See, what do you mean by Lorentz force? It is very important concept. See, a charge Q moving with a velocity v bar in the presence of electric field E bar and magnetic field B bar experiences some kind of force that is given by F is equal to Q, that is charge, E bar is electric field, and that again Q is charge, V bar is velocity, and V bar is a magnetic field. So this force is called as a Lorentz force. Okay. So whatever the charge, that charge are moving with a velocity v bar in the presence of electric field and magnetic field. So that kind of force is nothing but Lorentz force. Is it or not? So that is equal to F bar is equal to Q into electric field E bar plus Q into V bar cross, in the vector formation it can be written as cross V bar cross B bar. So this force is called as the Lorentz force. So this expression for force was deduced by H.A. Lorentz, and it is based on experimental observation. So it is whatever the force that I have derived here, that is all under the, that is all based on experimental observation. They made some kind of experiment, so that's why they gave the expression for Lorentz force. So that force is equal to the charge Q moving with a velocity v bar in the presence of electric field E bar and a magnetic field B bar that experiences some kind of force that is called as a Lorentz force. Now coming to the concept that comes under this Lorentz force, that is velocity selector. Okay, that is velocity selector. Let us derive what do you mean by velocity selector. See, suppose some kind of charge is moving in a kind of any material. Okay, so it is used, velocity selector, it is used to select the charged particles having different velocity from beam of that velocity. Okay, it is used to select the charged particles. Okay, it is used to select the charged particles having different velocity. Okay, having different velocity which is from beam of velocity. Okay, see, now consider a positively charged particle, that is Q. Okay, a charge that is Q moving with a velocity v bar subjected to uniform electric field E bar and magnetic field B bar acting at right angles to each other. These three phenomena, whatever Q charge, that is V bar and velocity, and electric field E bar, magnetic field B bar, these all criterias must be perpendicular to each other, must be perpendicular to each other. So let us derive an example. Suppose it is a kind of positive charge, point charge, okay? It is having some kind of electric field that is in this direction, that is QE, okay? And also the magnetic field that is in this direction, and the velocity is in this direction. Is there any perpendicularness here? I mean, those are all right angles to each other. Those are all right angles to each other as shown in the figure. Is it or not? Is it or not? You can see the diagram here. Whatever the magnetic field, electric field, charge and velocity, charge with electric field, charge with magnetic field, and magnetic field, okay, and velocity, these are all perpendicular to each other, in that condition, magnetic force, okay, in that condition, let us consider magnetic force. Okay, magnetic force, that is F magnetic force, is equal to Q into V into B. This is acting in the direction, upward direction. Okay, upward direction. And also the force due to electric field, that is downward direction, that is acting downward. Okay, this is equation number 2. Now let us balance each other. Let us balance the force due to electric field and force due to magnetic field. From equation number 1, from equation number 1 and equation number 2, we balance each other. So here what we will get cancelled? Q and Q, this get cancelled. Is it or not? Q and Q get cancelled. The remaining velocity will become electric field per magnetic field. Is it or not? So for a given magnitude electric field E and B, magnetic field B, velocity is fixed. This is nothing but, so whatever the expression I have derived here, that is where for a given magnitude velocity, for given magnitude electric field and magnetic field, velocity is fixed. Is it or not? This is nothing but velocity is fixed for both electric field and magnetic field in case of magnitude. Okay, thus a particle whose velocity v is equal to E by B alone travels undeflected. Undeflected means they remain same there, they remain constant there, they will not deflect there, because for a magnitude electric field and magnetic field, velocity is fixed there, so there is no any deflection produced inside the material. Is it or not? So there is no deflection in the current. Is it or not? So a particle whose velocity v is equal to E by B alone travels undeflected. They travel without deflecting. So particles whose velocity differ from this value get deflected. Why? Because velocity may vary there. Is it or not? Okay. In the case of v is equal to E by B, particle will travel without deflection, but particle whose velocity differ from each other. So in that condition, the particles will get deflect there. Okay. So hence, if we inject a stream of particles, each of the same charge with varying velocity into a region of combined fields, we get a fine pencil of particles with a single value v. In other words, this arrangement works as a velocity selector. Okay. See the condition. These are all condition. Okay. This is all condition. See, suppose I have said you that suppose velocity is equal to the ratio of electric field to the magnetic field. In that condition, particles will travel without deflection, that is undeflected. Suppose there is some kind of velocity difference. Okay, there is some kind of velocity difference. So in that condition, particles will get deflected. If you consider an particle, n number of particles here. Suppose if you consider a stream of particles with varying velocity, okay, each and every particle has different velocities. In that condition, into a region of combined fields, we get the single value. Okay, pencil of particles with a single value of v. In other words, this arrangement works as a velocity selector. Why this all particles will move with a single velocity there? So this will happen because of the arrangement works as a velocity selector. Okay, so in the starting point of the velocity selector, I have said you that select velocity selector is used to select the charged particles having different velocities from beam of velocity. It will consider all the particles in a single array, so it will cause the velocity to move in the single value of velocity. Okay, is it or not? So this is all about the velocity selector. This is all about the velocity selector. So what are the application of velocity selector? Let us discuss it. Why? Now, applications of, they may ask you for 2 marks. Applications of velocity selector. Okay, first one is, it is used to find specific charge. Okay, velocity selector, it is used, please note down, it is used to find specific charge. It is used to find specific charge, and also it is used in mass spectrometer. Okay, it is used in mass spectrometer. So this is all about the important concept of velocity selector. Now coming to the next concept, that is magnetic force on a current carrying wire. Magnetic force on a current carrying wire. See, the phenomenon in which a current carrying conductor experiences a force in a magnetic field is called the magnetic mechanical effect of electric current. See, let us consider this point. Okay, this is a magnetic force on a current carrying wire. In the name itself, in the name itself indicates the phenomenon here. Is it or not? Okay, so if you consider any current carrying wire, what is the magnetic force there? Okay, now let us discuss. See, this is a kind of phenomenon in which a current, this is a kind of phenomenon in which a current carrying conductor experiences a force. Okay, the phenomenon in which a current carrying conductor experiences a force in a magnetic field, it is called the mechanical effect of electric current. Okay, suppose if you consider any current carrying conductor like wire, okay, suppose if you consider any current carrying conductor, that is wire, which experiences some kind of force, in a magnetic field, is called the mechanical effect of electric current. Okay, so this force on the conductor is a manifestation of the force acting on the free electrons in the conductor placed in a magnetic field. So this force, so whatever the force that experiences, okay, it is a manifestation of the force acting on the free electrons. So okay, so if you consider any kind of wire, it is having some kind of free electrons over there. Okay, it will make that force, whatever the force it experiences, that will make the manifestation of force acting on the free electrons in the conductor placed in magnetic field. Okay, now so let us discuss this. Suppose if you consider a kind of current carrying conductor that is placed in magnetic field. Okay, this is kind of magnetic field experiences a mechanical force. Okay, experiences a kind of mechanical force. So the magnetic of this force, the magnitude of this force given by, that is magnitude. In case of magnitude, we will write it as, which is the wire, it is having the length L. Okay, the wire PQ, it is having some kind of length, that is L, length. So the force, the mechanical force acting on the particular current carrying conductor, that is wire, that is equal to F is equal to BIL into sine theta. Okay, so let us consider this is as equation number 1. So where B is the magnetic field, I is the current, L is the length of the conductor, and theta is the angle between the direction of the current, and the magnetic field. Is it or not? So this angle theta. See, suppose wire is placed like this. The direction of the current is always from Q to P. Is it or not? The direction they have shown here. The direction of the current flow is in this direction only, from Q to P. Is it or not? But that current direction and magnetic field are mutually perpendicular to each other. I mean, in the they are crossing each other. Is it or not? So length is the length of the L is the length of the conductor, and theta is the whatever the angle that is between the direction of the current and direction of the magnetic field. Now in kind of vector form, we will write this as F bar is equal to I L bar cross B bar, I into L bar cross B bar. Is it or not? I into L bar cross B bar. Now, the force is maximum. When it is maximum, when theta is equal to 90 degree, the force is maximum when theta is equal to 90 degree, because sine 90 degree is equal to 1. But it is minimum when theta is equal to 0 degree. Or sine 0 is 0, and also sine 180 degree is also 0. So that is when current carrying conductor is placed at right angles to the direction of the magnetic field, the force becomes maximum. Whatever the mechanical force, that will become maximum. Okay, the force exerted is 0 when theta is equal to, I have said you, the force exerted is 0 when theta is equal to 0 degree or 180 degree, and that is when a current carrying conductor is placed parallel to the direction of the magnetic field or anti-parallel. Suppose if you keep this current carrying wire along the direction of the magnetic field, in this direction or in this direction, the magnetic field, okay, the direction of magnetic field as well as the length of, direction of the current are parallel and anti-parallel to each other. Is it or not? Okay, so the direction of the current and the direction of magnetic field become parallel or anti-parallel. So in that condition, the mechanical force will become zero. Okay, because sine 0 degrees 0 and sine 180 degrees 0. Is it or not? So this will explained by the direction of the force is given by the Fleming's left hand rule. Okay, Fleming's left hand rule I have discussed in the earlier classes. So what Fleming's left hand rule indicates? It states that stretch the forefinger, middle finger and thumb of the left hand such that they are mutually perpendicular, they are mutually at right angles. So if the forefinger shows the direction of the magnetic field, okay, forefinger shows the direction of the magnetic field and middle finger shows the direction of the current and thumb finger shows the direction of the mechanical force of the conductor. Okay, these are mutually perpendicular to each other. Suppose if you stretch the left hand, okay, suppose if you stretch the left hand like fingers as perpendicular to each other, the thumb, middle finger and also forefinger, they are mutually perpendicular to each other. Here thumb indicates the force, here thumb indicates the mechanical force and forefinger indicates the magnetic field, and that is B bar. That is, this is F bar, and current, and the middle finger indicates the current, that is I. Okay, so let me derive this magnetic force on a current carrying wire by taking another example here. Let me take you to the in detail explanation. This is very important for 5 marks. See, magnetic, whatever the mathematical expressions come under this, let me derive. The magnetic force, I hope that concept is clear to you. Let me explain in detail, okay. Magnetic force acting on a current, please note down this, current carrying conductor in external magnetic field. External magnetic field, that is uniform. See, magnetic force acting on a current carrying conductor. Okay, let me discuss here. So consider a conductor of length L. So let me derive the same diagram. This is some kind of magnetic field. Okay, this is some kind of magnetic field. So let us discuss a kind of wire here. So this is a wire. So let us consider this is point A and this is point B. So which is having the length L. Is it or not? So consider a conductor of length L and area of cross section, that is A, placed in an external magnetic field makes an angle that is theta. Or let me discuss, this is P and this is Q. So that area having whatever the area of cross section, that is A. Let me discuss here. Area of cross section, that is A. Okay. So now this is the direction of the magnetic field. Okay. So this is the direction of the current. Okay. Now n is the number of electrons. Here let us consider n, small n. It is the number of electrons. Okay, present in the number of electrons present in the unit volume of the conductor. Present in the of conductor. So N is equal to becomes total number of electrons present in the volume of the conductor divided by the volume of the conductor. Okay. Now the total number of electrons present in the unit volume of the conductor. Okay, this total number N. Now the total number of electrons present in the unit volume of the conductor, that is equal to the N into volume of the conductor. Please note down this. Volume of the conductor, that is equal to N into volume of the conductor, that is area, cross section area, that is A, into length. This is equation number 1. Now the total charge present in the conductor. See, I have derived this total number of electrons present in the unit volume of the conductor, that is equal to N into volume of the conductor, that is area A into the length L. Okay, so now the total charge. Okay, the total charge present in the conductor. Total charge present in the conductor, that is Q, is equal to NaL into E. This is equation number 2. Is it or not? See, the total charge present in the conductor, that is Q is equal to NaL, or this is also equal to NaL. So that NaL into the charge, electric charge. Okay, this is equation number 2. Now current through the conductor. Okay, please note down this. Now current, that is denoted as I. Okay, current through the conductor, that is denoted by I is equal to NEA into VD. In terms of drift velocity, I have derived in this second chapter. Is it or not? Now, so we want VD here. Drift velocity, that is velocity, becomes I divided by NE into A. So this is equation number 4. Okay, so this is what velocity. Now what is the Lorentz force acting on the conductor? So whatever the mechanical force acting on the conductor, so whatever the force acting on the conductor, that is F bar is equal to Q into VB bar cross B bar under the kind of magnetic field. Is it or not? So this is equation number 5. Okay. Now, so substitute what we know, that according to mechanical force, that is Q into VB bar cross B bar. Is it or not? So in the magnitude, it can be written as F is equal to Q VD into B into sine theta. Is it or not in magnitude? So this is equation number 6. Now suppose if you consider what is the value of VD and what is the value of Q, you will write from equation number. See, if you consider what is Q here, so from equation number 2, that is Q, and from equation number 4, if you substitute, okay, Q what is Q? NaL into E. Is it or not? And what is VD here? I divided by Na into E. So from equation number 4, is it or not? NEA. NEA, is it or not? VD into B into sine theta. Here n get cancelled, a get cancelled, e get cancelled. So what is the remaining terms? That is I L B into sine theta. Is it or not? I L B into sine theta. This is in magnitude. This is the expression for mechanical force, or in vector form it can be written as F bar is equal to I into L bar cross B bar. This is the expression for magnetic force acting on the current carrying conductor in external magnetic field. Is it or not? So I have said you the two cases. The two cases. Suppose case 1. Please note down it. So what is the formula? F is equal to I L B into sine theta. Is it or not? Where when theta is if, okay, if theta is equal to 0 degree or theta is equal to 180 degree. So I have said you that magnetic field are in this direction. Okay, if you place the wire in this direction, okay, in this direction, that is P and Q having the length L, and the direction of the current, that is I, and the direction of the magnetic field, that is B bar. So in that condition, F is equal to IL B into sine 0 degree. So what is the condition here? Sine 0 is 0. ILB into 0. The force, the mechanical force will become 0 because it is parallel to the magnetic field. When the current is parallel to the magnetic field, so in that condition, or when the electric field is parallel to magnetic field, in that condition, mechanical force will become 0. Is it or not? Is it or not? So now, if you consider, see, suppose if you consider theta is equal to 180 degree, that is anti-parallel, the magnetic field in this direction, is it or not? Magnetic field in this direction, suppose the wire, this is wire if you place, and the direction of electric field, I mean the direction of the current, that is anti-parallel to the magnetic field, this is P and this is Q, sorry, this is actually P and this is actually Q, having the length same. So it is anti-parallel to the direction of the magnetic field. If you put the mechanical force, that is ILB into sine 180 degree, in that condition also the force will become 0 because sine 180 degrees 0. Okay, so this is the case where if you substitute or if you keep the electric field current carrying conductor parallel or anti-parallel to the magnetic field B bar, so in that condition what will happen? The mechanical force, whatever the mechanical force, that will become 0. Is it or not? So now suppose case 2. Case 2. So what will happen here? In the case 2, if the current carrying conductor, wire or a wire, it is placed perpendicular to the direction of the magnetic field, or the electric field in the direction of the magnetic field, in that condition, suppose this is a magnetic field, suppose the wire is kept like this, that is perpendicular to the magnetic field, not exactly perpendicular, but it is somewhat perpendicular. Okay, it is normal to the magnetic field. Is it or not? And so in that condition, ILB into sine theta, so force will become ILB into what is sine 90 degree, that is equal to 1. Therefore mechanical force will become ILB. This force is maximum. This force is maximum. Please note down this force, whatever the force, that is maximum. Okay. So let me revise the thing whatever said about the magnetic force acting on a current carrying conductor. See, magnetic force acting on a current carrying conductor in external magnetic field. That is, if you consider the magnetic field, the direction of the magnetic field and the direction of the electric field, that is current, and the angle between the direction of the electric field and angle between electric field and magnetic field, that is theta, the wire of length L, which is having the area which is equal to A. So in that condition, so the number of electrons present in the that conductor, it is equal to the number of electrons into unit volume of the conductor. Number of electrons into unit volume of the conductor. So that equation, total number of electrons present in the unit volume of the conductor is equal to the n into volume of the conductor. So that is n into A. This is equation number 1. So now the total charge present in the conductor, that is denoted by the letter that is Q. So if you substitute the total charge present in the conductor, that value will become NaL into E. So this is equation number 2. So the current carrying through the conductor, that is current through the conductor, that is in case of drift velocity, I is equal to NEA into VD. This is equation number 3. So suppose if you make changes in the equation number 3, the VD becomes the reciprocal of NEA into NEA. Okay, that is current divided by NEA. So this is equation number 4. Now the force acting on the conductor according to the Lorentz force, we will derive that force F bar is equal to Q into V bar VB bar cross B bar. This is equation number 5. If you substitute, okay, if you substitute in the magnitude of this mechanical force, the value will become IL B sin theta. So in the vector notation, it can be derived as F bar is equal to IL bar into B bar. So and I have derived the two cases here. So this is all about the magnetic force acting on the current carrying conductor in external magnetic field, that is B bar. I hope this concept is clear to you. Okay. So this is all the magnetic force on a current carrying wire and the related Fleming's left hand rule. So in tomorrow's session, I'll continue with whatever the concept related to your syllabus, I'll continue. So I hope these concepts are clear to you in this today's session. So let me discuss the further concepts in the tomorrow's session. So thanks for watching. Please don't forget to subscribe our channel and learn the things easily as quick as possible according to the understanding level, and start preparing for your examination part of view. So this may help in one or other way. I'll discuss in the next session. Thank you, dear students.